All right, guys, let's get into it. We're going to try to crank this little marketing campaign I'm going to do quickly here out as quickly as we can, and then we're going to jump into our presentation. So maybe Conrad, can you give me a thumbs up if you guys can see my screen there? Sick. Thank you. All right, guys, let's get started. So my name is Liam. I am the chair of the UVic IEEE student branch, and today I'm going to be giving you a small presentation on additive manufacturing. First, I'm going to tell you a little bit about the IEEE, as well as our student branch of the IEEE here, based in Victoria at UVic, some of the services we offer, and the workspace that we also allow our members to use. So a quick summary of both the IEEE as well as the UVic student branch specific benefits. We're going to start with IEEE Global. The IEEE is actually the world's largest technical organization. It has a membership of over 423,000 members now and counting, from the technology and engineering sectors, as well as actually business and finance now. So the IEEE is continuously expanding. One of the things that the IEEE strives to do is drive innovation through the use of technology and by connecting people around the world. And so they help you find opportunities and whatnot to change and modify and expand your career path and network with professionals from around the world. There's also a number of conferences they host year round, and they also mail out newsletters and whatnot to keep you up to date in your professional areas of interest. Some UVic specific benefits, so that's the part that we run. You get access to scholarships, which are only accessible to IEEE members within the Victoria community. So that is just UVic, since there's only one university in the area. Other than that, you also get access to our lab space, which is essentially a makerspace. It's also a microwave and whatnot, so you can keep yourself alive while you work in there for weeks on end as an engineering or technology student. It has lots of tools and whatnot as well that go along with the makerspace. And you also get access, priority access to these events, whether they're online or in person. A lot of our in-person events tend to book up almost instantaneously. Say like some of the soldering skill devs, we have to branch them over 2 days sometimes. So as an IEEE member, you get access to book whichever day would work for you for a specific event. Before essentially we send out the email to the mass engineering body. You also get to network with higher year students, say such as myself and whatnot. I'm a 5th year mechanical engineering honor student with a minor in business. And so it's really nice to say, ask me questions maybe about my particular profession or whatnot. We also have Conrad here, who's going into software engineering. And it's really nice to bounce ideas off of it. And also we can connect you with co-op opportunities and whatnot as well. But yeah, let's move forward. So I want to talk about some of our previous skill devs that we've done and some of the ones that we held this term. Maybe that can entice you a little bit more to join if you haven't already. We've done stuff on SolidWorks, electromechanical development, machine learning, Fusion 360, LinkedIn and whatnot, soldering workshops, like we said before, resumes and cover letters. And actually one of our, when we did a co-op on LinkedIn, 2 of the members that attended actually got high profile jobs through applying with their LinkedIn profile directly afterwards. So that one's up on YouTube if anybody wants to go watch that. Some of the things that we also did this term were a Robot C crash course, as well as this event right now, 3D printing and additive manufacturing. We also did introduction to soldering and a social night as well. So in the summer term, we're going to be hosting similar events, and you can look out for that. Moving on to our club space, you can see a few photos here. We have more of like a technical side, which is the photo on the right. It has all the electrical equipment, as well as now a 3D printer, 2 3D printers, sorry, this photo is a little outdated. It also has a compilation server and whatnot for running mathematically intensive operations. And then the photo there on the left, that one is more the social space. So if you're doing just studying whatnot, having group meetings, there's that little round table in the center there and the whiteboard. It's fantastic for brainstorming. It's also a coffee maker and a few fridges and whatnot, so you can store your lunch away and heat it up too if you need. Just a quick introduction to our executives so you can see any friendly faces around or ask anybody questions, say if you're passing in the hallway or if you come to the club room. I'm Liam, like I said before, I'm the chair. We also have Conrad, Tara, Declan, and Maddie. So yeah, Conrad's giving you a wave now. Moving on quickly, if anybody is interested in joining here, there's that QR code that will take you to your website. You can also sign up with the IEEE using the Future 50 discount code. I believe it will end up being about $17 per year, which is an absolutely fantastic price for what you get access to with this club room and whatnot, as well as the resource opportunities and co-op help. So without further ado, and I assume nobody has any questions, we will move on to our event today, which is Introduction to Additive Manufacturing. Just give me a small moment to line up our presentation. Cool. Conrad, can you give me a thumbs up? Sick, thanks. All right, guys, let's get this underway here. So today we're going to be talking about additive manufacturing and specifically 3D printing. There's lots of methods of additive manufacturing, and 3D printing is one of them. And we're going to be talking about a specific type of 3D printing. So let's move on and get into it. So there's a few methods of manufacturing. There is primarily subtractive manufacturing and additive manufacturing. And subtractive manufacturing has been the main method of creating parts from metal, wood, plastics, or ceramics, and many other materials since essentially the dawn of manufacturing. Traditionally, custom machining is an incredibly expensive method, though, since it requires lots of tools and fixtures and whatnot to create these custom parts. This typically requires a human to insert, maintain, and adjust these parts regularly, and that can get incredibly expensive for these custom parts. So while subtractive manufacturing is still superior in tightly tolerance or precise parts, the flexibility and aptitude to achieve complex geometries in additive manufacturing is a fantastic option and resource for design and manufacturing and for rapid prototyping purposes. I find specifically for rapid prototyping, it really helps, say, if you want to make visual aids for presentations, say if you're doing funding proposals or seed funding proposals. It's also fantastic for generating actual complex 3D parts. So some multi-body assemblies actually can only be made with methods of additive manufacturing because the geometry is so complex. And so when additive manufacturing became a very wide and well-known not too long ago, the doors essentially were unlocked to new mechanical systems, which was pretty fantastic. Other people also refer to the uses of additive manufacturing as agile tooling. So you can actually create hydroforming molds, you can create stamp molds, and you can create plastic injection molds or dies using 3D printing. So essentially what that is like you make a negative or a positive of a shape that you want, and then you can essentially stamp, mold, or inject or hydroform using that plastic, sheet of metal, or acrylic or whatnot that's been heated. And so it's a fantastic way to prototype essentially dies. So let's talk about the categories of 3D printing specifically. We got FDM at the top. This is the most common and cheapest form of 3D printing by far, and will be the primary focus of our presentation today, since that's what we primarily use in engineering and in the technical side of things. So what it does is it creates parts layer by layer by depositing melted material or filament, which is essentially the plastic that it uses. FDM also requires little to no post-processing. Next one we have is SLA. SLA creates parts from baths of resin using a high-intensity LCD or OLED screen. And what this does is it activates the resin into a hardening process. So an initial layer is created onto a build plate that is continuously extracted away from the screen in an orthogonal axis from the surface which the part's created. And then essentially, since it continues to extrude it, the part forms. SLA can generate parts with extreme detail, and it requires a fair bit of post-processing and curing and cleaning. You need to wear gloves and whatnot for handling green parts or hot off the press parts. And it's also fairly stinky. However, it is the second most common form of at-home or 3D printing in general, since it can it is fairly more expensive than FDM. However, its level of detail is significantly higher. So SLS type printing is a selective laser sintering, and it uses a high-powered laser to sinter or weld small particles of polymer together. These machines are typically much larger than those of FDM or SLA, not only due to the power requirements, but also due to essentially it needing to be able to shift around these particles. However, the bed size actually can be significantly larger given the geometry of the internally placed components. The output quality of these printers is also much better than those of FDM, and the speed is much better than SLA. However, it's much more expensive than both, and these are usually only used in the professional setting. They're often used to create incredibly complex and strong high-end user components, say one-off. So these could be used, say, like in F1 or in racing bikes, etc. So if you need to create very strong and one-off plastic components, this works very well. Also, moving on to MJ now. This is material jetting. So this uses ejected liquid polymer droplets and cures them with a UV light. So unlike SLA, this one creates geometries based on geometries based on light location. Material jetting creates geometry based on where the materials and the particles are put themselves, rather than where the light is directed, which is interesting. And these machines are the largest of the ones that we're going to be discussing today, and they're typically used by machine shops for one-off or low manufacturing quantity parts. A last one that we're going to be talking about today, and one that I will probably never touch in my lifespan since they're very expensive, is EBM. And these ones are essentially used for 3D printing metal. And what they do is there's a beam of electrons that is used to heat and melt pointwise particles of metal, and it fuses them together layer by layer, particle by particle. So this is a very rapidly expanding technology now, since strides have been made in the last 10 years to essentially allow this to be used by medium to large business. It's now used in many applications in industry, whether this is like by F1 or, whether this is used by, like F1 and whatnot, say for their brake calipers. A good example of this and prototype technology was Bugatti made a brake caliper. You guys might have seen this about a year or so ago. But this is a fantastic technology to start educating yourself about if you want to go into the world of additive manufacturing and perhaps pursue it professionally, because this is going to get really big in the next 10 to 20 years. We're going to start seeing it in small business too. Okay, so like I said before, guys, we're going to be talking specifically about FDM printing today. It's the cheapest and most common, so that's what we're going to be focusing on. And along with it being the most common, and given the nature of 3D printing in a three degree of freedom space, our geometries for these printers are relatively limited. You can see in the photo down there on the right, we have Cartesian and delta. So essentially, like we have different coordinate systems in mathematics, how we have like polar and Cartesian coordinates, it's the same thing here with printers. We have Cartesian, where a motor will drive each axis for Cartesian. So you can essentially move along a single axis for only moving a single motor. And then in the delta equivalent there, essentially all three motors need to be moving at a time to move the printer in a Cartesian coordinate direction. One thing to note with the Cartesian printer that we see there, where the four arrows are on the bed, that bed is actually where the printer will print the component. So one small thing if you are picking out printers is that if your bed actually moves a lot, specifically in the X and Y directions, that bed movement can create large inertial forces on your part if it's a heavy part. And so this photo here is relatively out of date, and a lot of printers have actually moved to a static bed where the bed won't move to create those inertial forces, and it will only be the printer head that's actually moving. And you can see an illustration of the printer head on the left there. where the filament, or essentially the wire of plastic, enters from the top, and then there is a heat extruder there with a heat exchanger, and then the liquid plastic is deposited layer by layer onto the previously printed material. And one important thing to note is that the plastic is heated to a very specific temperature. And there are a number of materials that you can get for printing with FDM. And each one has its very specific temperature because you want to push it just past its glass transition temperature. And so we're going to be talking a little bit more about the materials later. I won't touch on temperatures, and that will be up to your own research if you want to get into this. But it's one thing that you really need to pay attention to. Just a few more things here quickly about the FDM printing style and configuration. FDM is incredibly fast compared to other alternatives such as SLA. You can print components in probably about 1/10 the time. There's also a very wide variety of materials. This is due to it being the most popular form of 3D printing as well. However, depending on the printer that you get, specifically as a hobbyist, your part quality may be relatively low depending on the printer that you source, as well as how finely you tune the printer. If you don't spend any time tuning it, parts aren't going to come out that pretty. Also, since the parts are generated layer by layer, essentially between the layers, you have a shear plane. So if you put tension between two shear planes and try to pull it apart, that is the point which it is weakest. We're going to be looking at some design theory in a little bit. That we'll talk about that a little bit more, but it's one important thing to note here. These printers are also relatively high maintenance, especially at the hobbyist level. You need to keep the beds incredibly clean or else you'll have adhesion issues. And one more thing, it has relatively large tuning requirements. This comes in the form of the Z offset, which we'll talk about in a little bit. It's essentially when you're printing your first layer, what is the distance between the print bed and the nozzle? That's really important. So before we get into design theory, let's talk a little bit about the components so you guys are familiar with the printer. This is a little bit of an older model here. However, it was really nicely labeled, and so I decided to pull this one. The credits for all these images are in the references, by the way. So let's start with the motors here. This is a Cartesian 3D printer, which is the most common, and you can see the Z-axis motor here. This one drives a screw, which essentially moves this entire gantry up and down. There's also rods that are there for alignment. You can see those vertical rods. Next, you can see the Y motor, which is actually in the back here. It's underneath the bed, and it drives the bed back and forth in this direction here. Again, along these guide rails here. Then we have the X motor here, and the X motor drives a belt, actually, which is attached to this gantry here, and it moves the whole print head back and forth this way in the X direction. Other important components are the power supply. Usually that's where you'll find an on switch for your 3D printer. You'll also have the extruder motor here, which is another stepper motor, which is attached to the gantry. There's different types of FDM printers. Some of them are Bowden, where they have essentially a tube that goes from your print head to somewhere else on the printer, and the extruder motor will be up here. But this one is direct drive. That's the term. There's also a number of fans on the print head itself here. That's to cool down the plastic as soon as it essentially comes in contact with the previously printed layers. Of course, we have the print bed here, which we previously referred to. And there are also a number of limit switches in various locations so that when you first turn on your printer, the printer can find essentially its home coordinate position. I believe that's all we need to cover from here, guys. So why don't we talk about materials now? I really like this particular slide here. I also like this printout. So let's dig into it. Starting off with PLA. PLA is often considered to be the easiest to print, and it's also by far the most common printing material. It has fantastic bed adhesion with relatively low thermal expansion. So if your bed changes temperatures, it won't crack off and whatnot. It's also based off of starch. So one, I wouldn't recommend eating it, but two, it doesn't last as long, say, as like a plastic water bottle. So you can feel a little bit better about printing with this material. However, since it is based off of starch, and the binding materials aren't as strong as you would see in a material like PET, extended exposure to water or UV rays can break down the part significantly. One of the nice things, though, about it being the most common material is that it comes in many colors and finishes. You can get some that are shiny, you can get some that are matte, you can even get some that replicate wood. And so you can easily see from a Google search on Amazon all the different types of PLA you can get. Next is ABS. This is considered to be the second most common 3D printing material. It has a much higher thermal expansion than PLA. And as a result, often when you're printing with this material, you need to have an enclosed printer so that its ambient temperature inside the printer doesn't change. And its ambient temperature needs to be relatively high, about 80 degrees Celsius. So other than having a high thermal expansion, it's incredibly resistive to water, unlike PLA, where PLA will absorb water, ABS won't. And so this material lasts for a very long time. And also many consumer grade products are actually made out of ABS, like a desk fan or whatnot, or your light is typically made out of ABS. And you can get it in forms of ABS glass filled, which is essentially having different amounts of like fiberglass inserted into the ABS, which makes it stronger under tensile and compressive forces. So moving on to PET, this material lasts for an incredibly long time. This is what plastic bottles, plastic water bottles are made out of. And so it can come in a variety of colors and appearances as well. It's also shatterproof and incredibly chemical resistant. And you can get in food safe varieties as well. Hence it's used in water bottles. And it's a fantastic option if you're going to be working in the subsurface and marine industry. Okay, moving on to PETG. This is one of my favorite filaments because it's very, very adaptable to your situation, which you're going to be printing it for. It's incredibly impact resistant, it's chemical resistant, it has incredibly low water absorption as well, and it's resistive to UV rays, and it won't break down if it's in the sun. It's also fairly easily formed and die cut. PETG was essentially the iteration of PET, specifically for the purposes of manufacturing and 3D printing. It's pretty much better in every way. However, it is a little bit more expensive. Now, the last one I'm going to be talking to you guys about today is TPU. So this is a flexible filament, and it's often used for phone cases and whatnot, or overmold, say on your power tools, how you have like a grippy surface. It's very often a type of TPU, or, you know, the 6 blends of herbs and spices of TPU. So it's a fantastic material to print with. However, one note, if you do want to get printing with TPU, you cannot have an FDM Bowden drive setup. Your extruder has to be a direct drive system. Okay, so moving on for materials, guys, we're going to be talking about the design and printing process. And there's essentially 3 components. For making custom components, you're going to spend a little bit of time designing your component, employing design theory for additive manufacturing, and specifically FDM 3D printing, since that's what we're going to be talking about and have been today. We're also going to be talking about the slicing process. So that is the process of taking a component and dividing it up into layers for the printer to essentially look at and print. And then specifically the printer, we're going to be talking about some of the settings that you can use in your printer to get the optimal results and things you should look out for. All right, so let's talk about design methodologies. My favorite. Okay, so I recently spoke about the shear plane orientation with FDM printing. Since the printer prints in a number of layers, the junction between these said layers is often the weakest part of the print. And so you can see there's a few illustrations in the bottom right of this slide here. Those arrows represent forces acting on the part. And you can see the figure illustrates when the part is weak and when it is strong. And essentially, a single layer of a 3D printed component is strong if it's in tension, if you pull it across its axis. When you have multiple layers stacked up and you pull that part in its orthogonal direction, so a direction which is perpendicular to the plane that was just printed, it is incredibly weak. So one thing when you're setting it up and you're designing your component in CAD is you want to avoid features which would essentially force you to have to create a part which would take compressive or tensile forces in one of these directions here. Another really nice thing that you can do, and it is nice to employ in your design methodologies toolbook, is compliant features. So this part that you see here in the bottom left is actually a compliant vibration dampening holder, I guess you could say, that I designed a few weeks ago for my Mac 400 project. It employs bendable features, which essentially allow it to wrap around a specific profile. You can create these bendable profiles with a number of plastics. Specifically here, I designed it for PETG, and it's essentially just a very thin profile that will adapt to a surface. One thing when you're designing these bendable components is always make sure that the extrusion direction is orthogonal to the plane in which the bending is going to be induced. When you try to bend something, when it's weak or when the layers are stacked up in the bend direction, it will very often start to delaminate and you won't notice it right away, but your part will have a critical failure. Okay, so let's talk about tolerancing quickly. Tolerancing is essentially, okay, if I design it to be 5 millimeters wide, what's the printer going to make it? If it's 6 millimeters, then I am over toleranced by a millimeter. And depending on the printer, your tolerances are going to be better or worse. One of the printers that I most often use is called an Ender 5 Plus, and it's relatively cheap, and I have it tuned up well though. However, its tolerance is still about a millimeter. So if I want a part to be exactly 5 millimeters, often I'll shrink it by a certain percent of its original size, or I'll decrease the part size to about 4 millimeters. And that way I'll actually get the size that I want, which is 5 millimeters. So unlike laser cutting, where you have a curve, 3D printing usually makes parts bigger, which is an important point here. Also, if you're planning to print threads on 3D printing, a very good trick that I've learned is that you shrink parts essentially about 2%, or you make them bigger by 2%, either or works, in all the directions except for the axially threaded direction, and then your threaded prints will work quite well. Other things that you can tune are specifically like your temperatures, of course, which I talked about before, which is material based, Z offset and whatnot. We're going to talk about that more in a little bit, etc. And there's a bunch of different applications for that. Yeah, I think that's all I want to cover on this slide, besides the photo at the top there. If you do decide to get into 3D printing, I highly recommend that one of the first things that you do is you do one of these 3D printer tests. You can find the files for one of these on thingiverse.com, thingy with an I. And essentially what it will alert you to is what your printer is capable of and what it isn't. There's a bunch of tests here, say like the overhang tests, the circularity tests, form tests, as well as bridging tests, which are all fantastic to perform. Okay, moving on to our second step here, guys, which is slicing. This is the process of taking a solid 3D component and essentially translating it into a language that the computer can read and then print. And so what the slicer will do is we'll take a component and slice it up into a bunch of layers. And then each of those layers will be printed by, you guessed it, the 3D printer. And there are a lot of parameters that you can essentially tune here and change to your liking, depending on the wants and outcomes that you'd like for this particular part. Some of these are layer thickness, and you can see there on the image on the right, this is taken from a screenshot in Cura, which is a slicing software, and I can show you guys later how to install and use that if you like. So you can set the layer height. 0.16 is very common. It's a dynamic layer height. People will go up to 0.2 and actually 0.4 millimeters if they have to print quickly or the part resolution isn't that important. There's also things such as like wall thickness. So if you need your part to be a little bit stronger, you can increase the number of walls. So that's essentially how many times you have the printer going around the perimeter of the part and making the wall strong. Since the printer does not completely fill up the part with plastic, you can set the infill to 100% to make it solid. But if you only want the interior volume of a part to be partially filled, you can set it anywhere from 0 to 100% infill. And it will create a number of essentially looks and structures of infill. We can talk about this a little bit later as well. Other things are essentially the temperatures, which we've talked about before. So of course, your print head and melting the PLA or plastic, whichever you're using, that has to be a very specific temperature. But the other specific temperature you have to be worried about is actually the bed temperature. And most 3D printers, their beds are actually heated using resistors underneath the bed. And this is so that the materials will stick better. A lot of the materials, specifically PLA, PETG, and ABS, will stick better when they're heated to a higher temperature. And so you want to achieve decent bed adhesion, or else your printer or your part will pop off mid-print. And of course, your printer won't know that. And so you'll essentially be wasting plastic until your print is finished. Other things we can talk about are overhangs and supports. So in this photo down here in the left, you can see that this vibration dampening mount, which I mentioned earlier, there are overhangs here essentially. So there's components that are just sitting there above the 3D printing surface without anything below it. And that is essentially a no-no in 3D printing. You can't have your printer just print in free space. There wouldn't be anything to hold the plastic in place. So the use of supports will essentially allow you to print at a location where you wouldn't have been able to otherwise. What a support is essentially you can have a different material or the same material of plastic, and it will build up essentially to the level where your part is, a smaller geometry and optimized geometry part, which you can just tear off at the end. And it essentially just allows the first few layers of plastic in the location, which is overhanging, to be laid down very nicely. So once you've done your slicing and you've converted the file type from a part file to a G-code file, which is essentially the path that the printer will follow, you set it up for printing. And there are a number of things that you need to do for specifically FDM printing. You need to level the bed. So unless you have a bed leveling system, you need to have your bed exactly orthogonal to the Z direction of the printer. If you don't, your print head will actually run into the print bed in certain locations, and that is not what you want. Your distance between the bed and your print nozzle needs to be very exact for the first few layers, or else your part won't have decent adhesion and it won't turn out very well, and ultimately you'll be quite unhappy. So that's one thing you need to make sure is fantastic. Other things are your hot end speed. So hot end is essentially referring to the printing mechanism where the liquid plastic flows out. Sometimes different materials prefer to go faster or slower, or be cooled faster by the fans. And so you need to adjust that for each individual plastic or component you're printing. However, each printer usually has a favored setting that it likes. So you don't want to strive too far away from that favorite setting. Typically, I can find with an Ender 3 or an Ender 5, which are very common printers, you can go about 250% the rated speed or the default speed of the motors without having much of a problem when printing. Another thing is material flow. So sometimes your material, its diameter of the filament that's going into the print head is a little bit off. And since this is essentially an open loop system, the printer knows that the diameter of most filament is 1.75 millimeters. However, it's not actively measuring that. So perhaps your printer or your filament, or you got a roll of filament that's 1.65 millimeters, and you want to account for that. you can turn up the flow setting on your printer to essentially tell it to push more filament through the nozzle than it would be normally. And that could account for the discrepancies in diameter. Other things you need to be worried about are thermal contraction. So say if you like to print with ABS, you need an enclosed print area, so you don't want to have your temperatures changing. This would cause your part to crack and deform in certain areas, and that is obviously not what you want. We just have a few photos here of parts being actively printed. The bottom left one there, this is an industrial printer and it's printing some very thick layers, but it's a good illustration for the plastic being laid down. And then the bottom right here, you can also just essentially see the path that filament takes. The distance between the little Yoda head there and the extrusion head is obviously magnified just for this image. So just talking about some popular 3D printers right now, the most common for a creator or a hobbyist like myself or a student, you know, is pretty broke, is the Creality Ender 3. They're fantastic for the price, great printers, very quiet, and they do a fantastic job. Other great printers are, oh, I copied the name there and didn't change it in the middle. That is an Ultimaker S3. The middle one there. And we actually have a whole bunch of them in the mech lab at UVic, and they're fantastic. They require a lot less maintenance than the Ender 3 does, but they are about 10 times the price. So that is one thing to keep in mind. The Prusa i3 Mark III, that is a fantastic printer. It's very, very popular over in Europe. And spread throughout the whole world. The quality is better than an Ender 3. However, they are typically 2 or 3 times the price. And I forgot to mention, you can pick up an Ender 3 right now on Amazon, one of the older versions, for about $200. So it's quite easy to get into FDM 3D printing. Okay, I'm just gonna flash you guys the references slide here quickly so that everybody can see where I got my information from. And I am going to give you guys a live example of how to use the slicing software if you want. However, you definitely don't have to stick around for that if you're into it. So if you are planning on leaving now, thank you very much for sticking around for this whole presentation. I definitely had some run-on sentences. But if you are sticking around, we're just going to jump right into it now and do some slicing. Okay, cool. Can somebody give me a thumbs up if they can see this? Okay, sick. Thank you, Conrad. Okay, so this is what Cura looks like. We're at step 2 essentially in the 3D printing process right now. And this is assuming that we've designed a part and it's in an STL file saved, and we're going to import that now and take a look at some of its features. So we can just hit this little file over here to open up our file explorer, or you can just drag an STL file in, but I'm going to double click this guy here and open it up. So you can see it originates here in this orientation, and this orientation is specified from essentially the CAD design software you're using. And so obviously I don't really want to print this part like this. I don't think it would come out very well. And one of the things I talked about before was that parts that need to be pliable and compliant, so bendy, which is particularly this whole surface here, if it's bending, you don't want your bend plane essentially to be 90 degrees to your printing surface. So we need to reorient that here.
Test, please.
Ooh, Meg, I think you have your microphone on. If you have a question though, please feel free to hop on. The nice thing about not having hundreds of us here is that you can budge in whenever you want. Okay, so I'm going to run through what I would normally do for setting up a component for printing. And so the very first thing is obviously importing the part, which we've done. The next would be selecting what sort of material we're using. And that happens up here under generic PLA and material. So obviously we click this center tab.
1, 2, 3.
Meg, your microphone is still on there, buddy. And so we can select material here. There's a number of different materials you can choose from. These are all essentially specific to suppliers. However, I just always go with generic. A lot of these settings you don't really have to tweak. And then the other thing that you can choose is your nozzle size. So that is essentially the nozzle which the liquid plastic comes out of. And this is just so that the printer and the slicer settings know how quickly the print head has to move. So once those are set, often what I move to next is reorienting the part. I want to get it set up in its orientation that I'd be happy with it printing. So for this specific print, what I'm looking for is I want a decent surface area of this part that can adhere to our print bed so it doesn't rip off in the middle of printing. And I think I'm going to choose the base for this part. And the base happens to be right here. And so I'm going to click the part, which I just did, which selects it and highlights these different options that we have over here to essentially either change the scale, move the part around, or rotate it in space. So the rotation one is this middle tool here. So I'm going to click that and it gives us these options here. You can use the rings, which are right around the part right now to reorient it. Or you can use this tool here, the one on the far right. And what this allows you to do is just select a face which you want to be in contact with the print bed. So I'm going to select the bottom of the part and it just reorients itself into this position here. And I think that's the optimal position for this print. So I'm going to zoom us out and I'll walk you through the rest of the settings while we're here. The second one down is scaling. So you can scale the part by size here. There's also a uniform scaling checkbox, which you can use. So this is where you would scale a part if you had threads and wanted the part to thread well. There's also the moving option here, so you can move this around. And these options here are a little bit more advanced, so I think we won't talk about those today. So let's move into all of our printing settings here. So everything on the right here are essentially our advanced options, which is what I believe everybody should get familiarized with, since most printers, especially the ones that a student can afford, need a little bit of modification to be able to print well, and that modification always starts with the print settings. So continuing with the theme of just wanting to set up this part for printing, we're going to look at the layer height first. And so right at the top here, you can select a number of qualities, which is essentially the layer height. And 0.2 is a very standard quality item or thickness, and I think would be good for this print here. Typically, the print quality and the thickness don't really change the structural integrity of the part that much if you've oriented it well. So the next thing that we have here are walls. So these are the perimeters of essentially the part that is printed layer by layer. And I would be happy with 2 since this part won't take too much force. The next thing we have here are our top and bottom layers. And so essentially our top is the last layer that's printed and our bottom is the bottom layer that's printed there. And so essentially this would print 4 bottom layers, which means that it would be 4 layers of solid plastic on the bottom and 4 layers of solid plastic on the top. And that achieves both decent bed adhesion as well as gives you a nice surface at the top here. The next thing we have here is infill. So obviously this part isn't going to be completely solid plastic because 1, that would be expensive, 2, it would take a long time to print, and 3, it's unnecessary for this application. So I'm just going to quickly show you guys. We've set our infill here to 20%, and that looks like this inside the component here. So you can see we have our walls here, the red and the green, and then inside the orange there, that is the infill. So the interior volume of this part is 20% 20% plastic. And we've chosen to go with the pattern of cubic, which is essentially planes that rotate along 3 different axes. And there are a number of infill patterns, as you can see here, and each of them have different characteristics based on the particular application that you might be employing this part. You would want to choose a different infill pattern. Some are better in tension, some are better in compression, some are better for vibratory analysis and depleting vibrations, damping. So I would do your research into what infill pattern you would like. Often when you're printing with PLA and the part doesn't need to bear that much stress to, you can get away with 15 to 20% infill. So that's usually what I stick with. So yeah, moving on now, let's talk about material. So the material setting here is essentially what temperature are we going to be printing at. And this is the printing temperature at the nozzle. And I know for a fact that the PLA that I was using yesterday to print this exact part wanted a temperature from anywhere between 210 and 220. However, we know that when we were selecting the material earlier, we chose PLA and it chose 200 degrees Celsius for us here. And so that was essentially it, just assuming that we were going to be printing a PLA that wanted 200. But we need to change it within the range of the specific material that we were using. So I'm going to change this to 215. Cool. And you see the part goes gray here because I changed the parameter, and we'll need to reslice it in a little bit. So the next thing we can take a look at is speed. So that's essentially how quickly the printer is going to be printing this component and laying down bits of plastic. So the primary speed is 80 millimeters per second, which is a good speed. And the initial layer speed is 20 millimeters per second. So you always want to have a slower speed when you're putting down your initial layer onto the build plate, so that essentially the part or the little bit of plastic that you're printing at a time stays liquid for longer and can like ingress into the glass or textured plate that you're printing onto. Other important things are travel and whatnot. So you can talk about essentially your material retraction. You can play with this when you get a little bit more advanced. There's also cooling. So if you want your fans on whatnot, some materials like ABS don't require fans and others do. And this is generating support here. So we talked back in the presentation about how this part had these overhangs and we would want these supports. So I'm going to click on generate support here. And there's a number of options essentially that you can choose for support. There's lots of different structures. 2 of the ones that I have right now are just normal and tree, and we're going to go with normal for right now. And so you can specify your overhang angle. So essentially anything that would be printing at an angle of more than 45 degrees from vertical requires support, which is essentially what we're saying with these settings here. So we'll re-slice it in a second here and take a look at the preview so you can see exactly what the support would look like. Other things are build plate adhesion. So say if your part, you're having difficulty printing a part and it keeps popping off, there are a number of adhesion aids that you can add to your part to essentially allow it to print better. If you're not having any issues printing at all, you can just simply print a skirt, which is essentially a perimeter around the part, like just 1 or 2 passes. That essentially is just meant to like clear the nozzle of any contaminants. And then there's a few more options here that we don't really need to discuss right now. But what we're going to do now is, since we've entered in all of our settings into our quality manager here, we're going to hit the blue button at the bottom that says slice. So it shouldn't take more than a few seconds. And this is what the slicer shows us. Important things to note are down here in the bottom right-hand corner. It says with the specific printer that we chose, it's going to take 1 hour and 32 minutes to print. It will use 12 grams of plastic. And given essentially the diameter of plastic that we chose, or diameter of the filament, it will take 3.96 meters of filament to print. Moving on to the specific part now, you can see the part in yellow, red, and green, and then you can also see the support here in blue. And so that material, after the print is finished, will just rip right off. And this print we can take a look at in depth to diagnose potential issues in the print by sliding the slider down on the right-hand screen. We can see each individual layer, and that's actually a really good view of the infill starting at the bottom, that 20% infill. And we can go all the way down right to the first layer. And so you can see our first layer, like we noted earlier, it was going to be solid plastic in this particular component, and you can see that there. From here, you can directly save to a USB or a micro SD card that you can go plug into your printer and start your print. And it should have all the settings that you require. So that concludes the little demo, guys. I'm going to be here for another 15 to 20 minutes. Thank you so much for coming out to the presentation. If you have anything you want to chat about, any questions, maybe advice on purchasing a printer, please ask away. I'm going to be here for a while. Thanks, everybody. I appreciate your time.